All right, line R1, we're in learning task number 1, where we're going to take a look at the operation of discharge lighting. And the term discharge lighting might be a new term to you. You probably have heard of other types of lighting, like fluorescent lighting or HID lighting, which are all just going to be forms of discharge lighting. And discharge lighting just refers to the discharge of ultraviolet radiation that's going to be caused by collisions between electrons and between mercury. And we're going to take that UV radiation and we're going to go and safely convert that into visible light wave. All we're doing is we're shifting the frequency that it's going to be operating at. Let's start with a simple explanation of a fluorescent tube, because fluorescents are probably the most common type of discharge lighting out there. These days, fluorescents are getting supplanted by LEDs, which means that most of my discharge lighting in the future is probably going to be HID fixtures, you know, your metal halide and some of those other outdoor types of fixtures. But even those are getting supplanted once again by the LEDs. So it is a older technology at this point, but it's still very much a valid technology in what we take a look at. Let's go through what is actually happening inside of here. What we have is we've got a couple of main components. I'm going to go and highlight main components, then we're going to go and talk about the interaction that we are going to go and have. The first main component is going to be this setup that I'm going to have over here. We are going to call that our cathode. Now, we have a cathode at either end of every fluorescent tube. Not because we have got two negative points, but because we've got 2 points that are going to act as the negatives inside of our circuit. It is AC, which means that what we are going to have is we are going to have current flow through the tube in one direction for part of my cycle, and then we are going to go and have current flow through my tube in the opposite direction. So really, we've got two ends that are taking turns being our cathodes across there. The cathode itself is going to often be a bipin. We do have some single pins, but most of them are going to go and happen through the use of a bipin, because what we'll be able to do is we'll be able to go and create a voltage differential across here. I'm going to draw this end in over here. We're going to draw this end in the exact same way. And then I'm going to go and have this end over here. And what we're going to do across is we're going to place a small voltage drop. Remember, if I've got a positive, I have to have a negative, right? We can never have, you know, light without dark, positive without negative, etc. There's just some things that we need to have both of them together. So I'm going to start by designating this side of my tube as being the more positive end over here, and this end as being the more negative end. Now, there's a couple different ways that we can designate negativity, right? We've got just positive and negative, but then we've also got the concept of more. Like something can be more negative or something can be more positive on any of my ends. So what I could have is I could have a negative value of voltage that's going to be attached to this pin over here. Let's give this thing a value of, let's say, negative 110 volts that we have over there. But then I could make this other pin a slight bit more negative, 120 volts. And when I do that, I see that either side of this, you know, this pin over here or this pin over here is a negative, and they're going to be, you know, referencing to the positive over here. But I also see that from point to point inside of here, there is a difference. A potential difference. We would refer to this as a voltage. How many volts would I see across this filament? Well, I would see 10 volts across the filament, going from 110 negative to 120 negative over here, which would mean that I'm going to go and have current flow through that filament in the direction going from my most negative to my least negative. In reference to this section over here, this one is a slight bit more positive, okay? So we would have current that would travel through here, through this section, through here, and back up. We're going to start with this section that we're looking at over here. That current flow that is traveling through the cathode is going to go and give us what we refer to as our cathode preheat. If you have worked in the industry long enough, you'll be familiar with the fact that fluorescents sometimes struggle to go and get lit anytime that we've got too cold of a temperature. And the reason for that is that they need to have a certain amount of heat on the inside on their cathode. The cathode is going to be a coil. It's a little tungsten coil. It looks like a light bulb coil. That is going to go and have a small amalgam. Amalgam is just going to be a chemical compound made up of like sodiums and a bunch of other metallics that are going to be inside of there. And what happens is once we start to heat them up, those electrons that are in the valence shells of these materials that are the amalgam are going to get excited. And if they get too excited, whing, one of them, you know, will just go and fly off. And we call that emitting an electron. So if we can overly excite whatever we've got on the amalgam over here, and we do that through heat, then it's going to wing off these electrons. And those electrons, once we've got a free electron, that electron looks and says, this whole section over here is negative, that section over there is positive, and so that electron goes whoosh down the tube like that. And as it does so, it is going to go and strike into the occasional little bit of mercury. Hg over here is going to be my chemical identifier for mercury. So I'm going to go and have these electrons that are going to be traveling through the tube, and whenever they strike mercury, there's a reaction, right? For every action, there's an equal and opposite reaction. And energy can neither be created nor destroyed. It can only go and change form. So I had movement, potential energy, and then I'm going to go and have a striking over here, which is going to go and change that into a radiation energy. What we get is we get UV radiation that is going to go and happen. Now, ultraviolet radiation or UV radiation is dangerous for us. We don't want to look at that. It's not, good for your eyes or anything. So what we're going to do is we're going to go and phase shift it. We're going to move it from the very high frequency, ultraviolet radiation is super high frequency, to a much lower frequency, something that's going to be inside of our visible light range that we have. And the way that we do that is that we are going to be able to coat, well, we aren't going to be, but the manufacturers are going to coat the inside of the tube with phosphor. Phosphor is basically what we refer to as glow-in-the-dark stuff. All those little toys you had as a kid that would glow in the dark when you put a flashlight to them and stuff, had phosphors inside of them, and phosphors just radiate visible light when they get struck. So what we do is we strike these phosphors with this UV radiation, which super excites those phosphors, and then those phosphors are going to go and glow. But they glow off with a light that we refer to as warm white or cool white, or anything that's going to be inside of our visible spectrum. It's a complex, multiple changes that's going to be happening inside of here, but it's always happening continuously from one end of the tube over towards the other. And what we get is this, what we've just described in here with all these electrons flying in that direction, that's only going to happen for half of a cycle, right? 8 milliseconds. And then at that point, all my positives and negatives reverse, and then we start winging electrons in from the other side over there. Okay, inside of here as well, we do also have the tubes evacuated. If you've ever popped one of these by accident, they kind of make a sort of sound when they pop, and it's not because they're under pressure, but rather because they have been depressurized, and then we place in a small amount of other gas. We call it an inert gas that we would have inside of there. That gas is going to be a mixture of our neon types of gas. Neons are types of gas that will easily ionize and allow us to conduct electricity through the air. So we take out the regular, mixture of oxygen and carbon dioxide and, all those other things, and we replace it with argon, sometimes a little bit of neon that's going to be inside of there, sometimes we get a little bit of krypton. All of those are going to be ionizable gases, and those ionizable gases are readily able to allow us to carry those electrons through. That's our basic construction that we are going to go and have inside of here. All fluorescent lights, all discharge lights pretty much, but specifically fluorescent lights, are going to be creating UV radiation. How we get different colors out, what we refer to as warm colors or cool colors, the blue spectrum or the yellow spectrum, are all going to be based upon the type of phosphor that is going to be placed in there by the manufacturer. If they place in a little bit more blue phosphor, then we're going to have a little bit more of a bluish color. If they place in a bit more of the yellowish white, we're going to get a warmer color that we would go and have out of these ones. That's going to be the way that the bulb works. So what about the ballast? Well, the ballast is going to be used for a couple of different things. Inside of your binder there, it says that it is going to be used to create the high striking voltage. Sometimes, I'm just going to put that in there. We're going to call that striking voltage. There is going to be some sort of striking voltage that we need to be able to get from one end of the tube towards the other. A 4-foot tube is obviously going to have a lower striking voltage because it's only got a 4-foot gap compared to an 8-foot tube. 8-foot tubes are far more dangerous. There's a much higher voltage because we have to go and blast through 8 feet of gas rather than 4 feet. Some of those little 2-foot tubes hardly have, or they don't need any striking voltage at all. So our ballast in some cases is going to be used as a auto transformer or isolation transformer to go and provide a higher value of striking volts. My ballast is also going to be used as a choke. You remember that from back when we were going through A1 and A4, that we referred to ballasts and their ability to go and stop current through counter EMF. We refer to that as choking ability, right? So what we will do is we will use them as a choke, because otherwise, if I've got a good tube inside of here that has got good gases inside of it, really, I've got the potential for unlimited electrons to go and flow through here. We wouldn't want to have unlimited electrons flowing through here, because we would ultimately have to go and take them all from our supply, which would mean that we would have, unlimited current flowing through there. We refer to that as being a short circuit type of characteristic. So we will also use our ballast to go and limit our amount of current that we are going to go and have through here. And our very last thing that it is going to do is it is going to go and provide our cathode voltage difference. Remember how we had this over here? This is going to be a volts per turn thing. If you think back to auto transformers that we covered, remember how we talked about the volts per turn. All that there is a difference inside of our ballast. If I were to go and take a look at the ballast, and we haven't described ballast, and we're not going to need to in great detail, but basically this one would be coming off that turn, and this one would be coming off of that turn. And if I've got a 10 volts per turn, that's where I'm going to go and have that difference across there. So the third thing that a ballast does is it provides cathode voltage. And I'm going to actually call that provides cathode voltage difference. Let me erase that. Difference. Beautiful. So those are the three main things that we are going to be provided from our ballast. We'll talk about ballast a little bit later on as we go through the lighting over here. We're just going to kind of leave the bulb alone now at this point for the operation. We've gone through that. Now let's go and talk about bulbs themselves. So at the very top of your page above this, they talk about bulb shapes, and they talk about T12, T8, T5, T17, etc. And they don't really explain what those things are. But what they are is the number that we are going to go and see, or the size, is going to be 1/8 of an inch. So if I have got a T12, that means that that number 12 inside of there means that that bulb has got a diameter, or a distance across, that is going to go and be 12/8. 12/8, which, we can go and change that fraction into 1.5 inches. So it's a 1.5 inch diameter tube. A T8, you should all be quite familiar with T8 tubes. That's going to be 1 inch across, right? It's going to be 8/8, so it's going to be across. A T5 is going to be 5/8 across. That's going to be those skinny little fluorescent bulbs that we have. Lengths of the bulbs are going to go and vary. We have got some really, really tiny short ones that are going to be used generally inside of equipment, not so much for, lighting of installations, but we have shortest ones are going to be down to the 6-inch length. Usually they're going to be small ones that are going to be like bi-pins inside of other types. Oops, sorry, not that one. Stuff that's going to look like this, where we're going to have short little ones like that, usually U-shaped. Our longest tubes that we are going to have are going to be 8-foot tubes. Past that, it does not get feasible to really make longer ones. There might be the occasional specialty one, but it's not going to be a common usage thing, because anything over that really struggles with the glass that we are going to go and have, right? Somewhere over here, it doesn't talk about, the actual glass there much. They talk about it over here, but it's just that length, that we would need to have, and particularly that length that is going to go and prevent that implosion that we would have. All right, talking about the components, we have talked about this, the cathode. The cathode is going to be the same as the filament that we would have inside of a regular incandescent light bulb. It's usually going to go and be tungsten because it heats up really good, and it is going to be coated that we will have. We are going to go and have the phosphor inside. We talked about that one as well, that's going to pick our color of the bulb, and then we are also going to go and have the gas, argon, krypton, neon, stuff like that. That's going to be in there. Note that it is at low pressure. So we evacuate the tube, or suck out all of the air, and then we go and insert just a small amount of gas that's going to be inside of there. And then we are also going to go and have mercury. What do we know about mercury? Well, we know that mercury is a dangerous, dangerous substance that we are going to have. So be careful with these bulbs. Do not just smash them into a dumpster. If you do break one and you get the inside coating all over yourself, even if you don't visibly see it. Make sure you wash up before you go and eat, because it's just really harmful to be ingesting any mercury. It is a small amount that is inside of these, but it is still a dangerous amount if you get exposed to enough. That mercury that is inside of these does require these to be properly recycled as well. These are not dumpsterable types of components. You're supposed to take these into wherever you take your recycling, and they should have a lamp recycling place. It's a recovery place. Honestly, the manufacturers do want these back, because it's much harder to go and extract mercury out of the dirt than it is to go and extract mercury out of, that tiny little bit of materials inside of a crushed light bulb. So they want to go and get those back so they can get the phosphors, the mercury, and things like that as well. Okay. Yeah, moving on then, let's take a look at this chart over here. And let's bring up a new term that we have as well, which is going to be efficacy. You might have saw this in your pre-reading, right? Because you all did that. Efficacy. And you might have thought, look at those idiots. They don't know how to spell efficiency. You should have covered this inside of your first year materials, that efficacy is going to go and be the ratio of the lumens that I'm going to go and have out compared to my watts that I'm going to go and have for my input power. It's basically going to be how good is my lamp at converting power into light. We have some lights that are very, very poor at converting power into light. Take a look at an incandescent light bulb. Over 90% of what it generates is going to be heat, and only about 10% goes into visible light, which means that it's got a very, very low efficacy. These ones over here are going to have a much higher efficacy that we are going to have. Now, they don't give us, ratings, but it's a more efficient light for getting large amounts of light out of these things. They talk about power consumption, and they talk about the light output that you're going to go and have in lumens. They do a comparison here. A CFL of about a 9 to 13 watts is going to be equivalent to about a 40 watts incandescent. Now, these are coarse, rough numbers, and probably these numbers are much more finely tuned at this point. Incandescent technology is still advancing. We haven't just left it alone, been like, yeah, Thomas Edison, that was good enough. We're still working on making better incandescent light, though. There is still a market for it. CFLs, same thing. CFL stands for compact fluorescent, by the way, for those of you that have not seen that acronym before, compact fluorescent lamp. That's that section over there. But what we're seeing over here is that we're going to have about double the efficacy that we are going to have, right? Sometimes, double to about, 4 times the efficacy that we're going to get out using the fluorescent compared to my incandescent. Looking at bulb shapes, we should be very familiar with these ones here, the straight bulb shapes. We're going to have different ends that are going to be on them. There are U-shaped ones that are going to be generally seen inside of 2x2 troffer fixtures. If you've worked in the industry and commercial at all, you would be familiar with the concept of troffers. Troffers are going to be those fluorescent fixtures or LED fixtures that you're going to drop into a T-bar ceiling. Oftentimes, the U-shaped ones would then allow you to use the same 4-foot ballast, and they would just have a 2x2 grid, and they've got that bent out U-shaped bulb that's inside there. Circline is much less commonly used at this point. It's pretty much done out there. I don't know if anybody that still has them, but you might run into them in an old installation where they want to keep a few going. And then we are going to go and have our compact fluorescent lamps. And compact fluorescent lamps went through a bit of an evolution, and they start them out over here where they initially had these ones here that had a bipin over here that had an external ballast. If you ever saw these things in real life, they had kind of a flat pan shape. They have got a little stabby base over here. There's little pins off of those. You stab the bulb into that base over there, and then it gets connected over to its ballast. Through that connection, we bring power in. So the ballast was separate. Then what we started to do is they started to say, well, that ballast is really small, so we could place it inside. It was the same stabby light bulb. It's supposed to go and have that inside there. But then they had that screwed into there. It was a really heavy light bulb. Then they started to have some issues that, these things were getting too cold and they were unreliable. So they went for a while into these big cased light bulbs. And then they moved over to what we're much more, commonly seeing these days, which is going to be those twisted tube types of fluorescent. The twist of the tube just allows them to go and get maximum surface area so that they can get maximum light output out of these ones. There is a need to differentiate, though, between the ones that have got an integrated ballast. Anytime that I have got something like that, I can just screw those things into a regular Edison base. We refer to our standard incandescent base as an E26. E stands for Edison style, that's a screw base. 26 stands for a 26 millimeter diameter that we are going to go and have off of that. So these ones here that have got the E26 style do not use a ballast. Anything that does not have the E26 style, it probably has got some sort of a ballast, or in these days we start to call these things drivers. Pin ends, multiple different types that we've got. Bipin, which is really standard out there. Those are the ones that you shove them up into those tombstones. You have to give them the quarter turn at that point. Single pin, which are going to be a larger striking voltage. You'll note that the single pin has only got one point of contact. Therefore, it does not have a heated cathode. So in order to go and create the gas strike going across from one end of the tube to the other, they have to go to ridiculously high values of voltage. Some cases, there's going to be pins on the end of these things that the tombstones are going to be spring-loaded, so there's a switch inside. So that when you take one of these bulbs out, it is going to go and take out that switch as well. We've also got another one, which is going to be a recessed double contact. Uses the same type of spring-loaded bases inside of there, and it's got two sets of contacts that are going to go and make contact with it. A bit more reliable than the bipin. I think everybody by now has like broken one or two of these, where you're twisting them in and you snap off one of those pins, or it doesn't align with the tombstone. They can just be frustrating, particularly on low-quality troffer fixtures where the ends are sometimes even just like a bit misaligned. Okay, talking about operating characteristics and then about the lamps themselves, there is a pile of tables that are going to be inside of here. As with all tables, I do want you to go and memorize all of the data that is on all of these tables. I'm joking. We're not going to do that. That would be crazy talk. Let's talk about the operation. We are going to refer a little bit back and forth to these tables, but don't waste time trying to memorize tables. These tables are, first of all, going to be outdated at this point. They do have some useful information on them that we're going to refer to, just so we get used to reading tables, but in the field you're just going to go and find a current table for the actual light that you are going to be using. All right, let's talk about lamp characteristics though, starting right from the very beginning over there. Fluorescent lamps have got a long life expectancy. Anywhere from 7,500 all the way out to 20,000. And these days, we're up to about 30,000 that we're able to get on some of those. So it's a long lifespan before you have to go and replace it. Now, that means our lifespan does not necessarily mean useful lifespan, right? There's going to come a day where I'm going to be less useful as an instructor. I'll still be alive, but, maybe I'll be less useful because, I don't know, medical issues. There's, medical stuff that happens inside of every family, and I'm, particularly at the risk for a stroke in our family. So if I would have a stroke, I might still be alive, but I'm not going to be very useful. We get the same thing that's going to go and happen with a lot of our components, only it's not as easy to go and see. We've got what is referred to as LM70 ratings. LM70 is going to be lumen measurement 70% is what it stands for. This is a rating that you need to know because of every bulb, they're going to go and have a lifespan. That's how long it goes between when we can start this thing to when the thing is actually going to go and completely shut off. But the LM70 is going to be the useful lifespan. Basically, LM70 is going to go and tell you how long that bulb can operate for fluorescence and for incandescence and for any of my LEDs. It's going to tell you how long I can operate before I fall below that 70% rating off of it. And after that, we consider the bulb to be effectively done. It's still giving out light, but it's not great amounts of light. Everybody's seen this. You to replace the bulbs, and all of a sudden the customer's like, whoa, it's so much brighter now. They're like, but the other bulb was still working. Is it a new type of bulb? You're like, no, it's the same type of bulb. What was happening is the inside of that other bulb starts to go and have, buildups of tungsten that happens from the cathodes. And we start having the phosphor that starts getting a little bit weaker over time. It doesn't react nearly as strongly. The mercury that's inside of the bulb is unevenly distributed. There's just a pile of stuff that goes and happens. So you could have a bulb that is going to, and we'll say that this is a 20,000 hour rated bulb. And I've got two bulbs that have got a 20,000 hour rating, but if one of them has got an LM70 rating that is going to be good for 15,000 hours versus another one that is going to be good for 10,000 hours, that actually tells me that although both of these will last the same amount of time, this one halfway through is going to be putting out just a weak, poor quality light. Whereas this one over here, it's going to be about 3/4 of its way through its lifespan before it is going to drop below those values. Fluorescents do need to go and have long burning times. Fluorescents do not work well with instantaneous, starts and stops. If I were to go and take this fluorescent that I have over here, I'm just going to erase a bunch of the extra little things that I have inside of here. And if I were to go and turn this thing on and off rapidly, there's a couple of problems that happen. First of all, this tungsten, we're going to go and get inrush current. Tungsten has got a high amount of inrush current anytime that we have got it cold, and then it is going to go and settle in. But that causes a large amount of thermal expansion because it goes from having very coldness to being very hotness inside of this thing, which means that there's massive amounts of movement. That's where your filament breaks. Everybody's seen this. You know that a light bulb, an incandescent, well, I don't know, maybe you don't know at this point, but it used to be everybody knew that if a light bulb was going to burn out, an incandescent was always when you turned the switch on. It would all of a sudden just to go real bright, poof, and that was it. Because it was that expansion, that thermal expansion it could not handle. We're not supposed to be flipping these things on and off for the same reason. We're supposed to generally have an operating time period that is going to be a couple of hours at a time. If you can go longer, it is less stress because you've already got everything put in motion. It's always way harder on something to get it into motion than it is to go and maintain that motion. In our case, the motion we're talking about is going to be that switching back and forth of the electrons from one end to the other. It's easier for us to do or to maintain these bulbs if we go for long periods of time at a time, on at a time. You do reduce your lamp light by switching them to frequency. Operating with the wrong type of ballast, obviously, yes, you're going to have wrong values of voltage, either too high or too low, which is going to go and result in too much current, or wrong heater, cathode voltage that's going to be crossed here, etc. Using excessive supply voltage, too much volts, obviously, once again, a problem. And then losing cathode preheat during startup. In some cases, this cathode is going to go in through a little resistive component. So what I drew there before, we had this ballast over here, and we said that we were going to go and take that across that volts per turn over there. What happens in some of these is that there's going to be a little thermostat inside there. It's just a bimetallic strip thermostat that's going to be inside of there. That's going to be connected across there, and all that it is going to do is it is going to go and measure until we get enough current flow through it. It's not actually the thermostat that's sensing the tube, it's more that it's sensing the amount of current that's gone through this thing, and once this thing goes and opens up, it no longer runs current through that cathode, because at that point, it's already warm, and so those electrons are easy for us to go and emit. So if you lose that, this thing opens up too soon, or maybe it failed to close, you will not get that preheat on your cathode. Your light output on a fluorescent is also going to go and decrease. The initial light when you first turn them on is going to be super bright, but after that, it is going to go and taper off. About the first 50 to 100 hours are going to be your biggest drop off of light, and then after that, it is going to go and stabilize to 50 to 100, and then we're going to kind of stabilize, but it's always going down. Never getting better, always going down on these ones. You do also need to go through a period of what is referred to as seasoning. So the first time that you turn a light on, you want to go and keep that thing on as long as possible. If you got fluorescence, flip that thing on, close the room door, walk away from it, and just leave that thing on, even if it's running for the rest of the day, because your customer is going to be way happier at the end of the day. What happens is when this stuff is manufactured, when it's shipped, mercury is really heavy. So the mercury is going to tend to want to accumulate along the bottom, especially the vibration, that happens during shipping. If those things were stored horizontally or even vertically, all the mercury is going to end up at one end or the other. We need that to go and move out and across all the tubes fairly evenly. Once that seasoning has happened, you're going to go and get much better light output as well. And that whole concept of the mercury dropping to the bottom over here also happens during operation, where you're going to go and have striations, it's called, which is going to be like lines that you're going to go and have across the bottom. Those striations are usually going to be mercury that has fallen to the bottom. So what you can do is you just take your tube out and then flip it 180 degrees, whatever was the bottom part of the tube, you move up to the top again, and then all of that mercury, which has accumulated on the bottom, is obviously going to have to start moving through the lamp again. You get more light out of it. I mean, if you're coming in there for a customer, just replace the lamps if it's already getting to that blackening. But if it's in your own house and, your light's getting just a little bit dull and you don't have time to run down to the Home Depot to pick up a set of tubes or something, flip the tubes and it actually does make a difference. If you have got cold weather, ballasts tend to, not ballasts, but the lamps tend to go and work poorly. And the reason for that is that we need to develop just enough heat. I'm just going to go and reclose that one there. We need to develop enough heat over top of this cathode over here. If it is cold enough outside, it is just not going to be able to develop a sufficient amount of heat to start emitting those electrons. In those cases, what you do need to have is a special type of ballast. So if it's going to be either mounted outside, underneath an overhang, on a porch, or if it's going to be mounted inside in a cold place, like inside of a cooler or a refrigeration unit, you would need to get those cold weather ballasts inside of these. This is also going to be opposite to LEDs. LEDs do way better under cold temperatures than they do underneath hot temperatures. LEDs tend to go and lose their light output underneath hot temperatures. Fluorescents tend to gain light output underneath hot temperatures because we have a much weaker bond on our amalgam, and so we can more easily move those electrons back and forth. So in some cases, if you've got cold weather areas, don't stick in the fluorescent. Go for the LED because it's going to operate much better. Conversely, if you've got some place that's going to be wicked hot, like a boiler room or something like that, fluorescents might be your better long-term solution there rather than going LED. All right, ballasts themselves are going to go and last a ridiculously long amount of time because they're just going to be simple transformers. Some of them do have small switching components, particularly this cathode preheater, but that's usually going to be a plug-in extra that goes onto the ballast itself. The actual ballast itself is just going to be wound. If it does get too hot, like any other transformer, you run that risk of VOCs degassing. We talked about this in transformers, that you cannot go and allow it to get too warm because the insulation gets too weak and we lose those oily parts, the volatile organic compounds, and we start to go and have problems. The ballast should go and last 12 to 15 years is what the book says. It's not uncommon though to see ballasts out there that have been like a 20+ year operating life. Ballasts are also going to be graded based upon the type of noise that they put out. Everybody's heard a really hummy, bad, fluorescent at some point or another. If you had fluorescents that were going to be spec'd for inside of an office environment or inside of like a library or something, you're going to want to have something that's going to be really quiet, and so you're going to have to get a Class A ballast compared to a Class F, which you might use in a place like a gymnasium or something like that, where it's already noisy and you just don't really notice that hum in the midst of everything else. You will still get the same ballast for the type of tube. You might be looking at a 40 watts, 48-inch tube. There's multiple different types of ballast, but they're all going to operate the same, just some of them are going to be noisier than others. Rapid start lamps are going to be probably the most common that you will be dealing with at this point. They don't, take a long time. Some of our old fluorescents had to go through this probably about maybe a 2 or 3 minutes, process of running before they kind of came up to full light output. Rapid starts are going to go and be almost instantly full output. We do have a couple of other ones as well, a VHO and SHO for very high output and super high output. Those are going to go and be types of fluorescent lamps that operate at incredibly high values of voltage. If you see VHO or SHO, be very careful working around them because it's going to suck a lot if you get shocked off of one of those ones. They also talk about the slimline. Slimline is going to be just a name for ones that have got the single pin end. These ones over here. They're an instant start lamp with a single pin at each end. That instant start lamp operates at ridiculously high values of voltage, and what you will have is that there should be a switch where your power comes into one of those tombstones at the end. That's going to be a spring-loaded in tombstone, so that here's the cup that pin goes into, and if I draw this, so that's my tombstone inside there. That wire goes up on the inside. When I press this lamp into this tombstone, what it does is it moves that cup back, and then that cup allows it to actually make contact with the line in. Let's draw that like that. When we go and insert that inside there, and then that line in is actually carried through into the actual ballast, so that when you remove that lamp, the ballast should be dead. Now that's provided that lamp is still wired correctly. If people have been screwing around with the lamps and changing them, and if they've changed the ballast, when somebody that doesn't know what they're doing takes out a ballast, there's multiple different ways you can rewire those ballasts, but not all of those are going to be the same. Some might work, they're just going to be dangerous. So be careful. If you open up, one of these ones and there's a visible, that you can see the morettes in there, somebody has taken those ballasts out and changed them, make sure that you are going to, be careful with that and that you're not exposing yourself to high values of voltage. We do have a couple of other types of specialized fluorescent lamps. The other ones that they're going to talk about are going to be germicidal or black light ones. Black light ones are going to go and have a weak amount of phosphor. It is still going to be a phosphor coating, but it is going to go and change all of my UV radiation. It's only going to slightly shift it, so it's just barely within our visible range. That's why they get that purplish sort of glow. And then we're also going to be able to take that, little bit of glow and we place anything neon underneath it and it tends to glow. They're not generally used inside of, lighting outside of clubs or places like that. Where we do use them is we sometimes will use them in manufacturing because they allow us to highlight imperfections. If you've got a piece that has been milled that has cracks inside of those cracks are going to pick up contaminants, and those contaminants are going to go and glow inside of them. So we will use them for that. You'll also see, some of these black lights being used to go and pick up invisible inking marks. A lot of our components actually have got invisible inks that are going to be on them that are used during manufacturing, to go and identify stuff. But when the consumer gets it, they want to have a nice plain looking component. So they don't want to see any of the inking, but when it's going through the factory floor, we need to read that. So we'll have them used for that. There is other ones that have a stronger UV that are going to be our sun lamps and our germicidal lamps. Germicidal lamps are going to go and be used to kill bacteria. It turns out that, we can use UV to kill the cove. We just can't really put it out there because it would also kill humans. It's not very good for you to be exposed to these germicidal lamps. But high amounts of UV radiation, what it does is it basically causes cancer inside of the bacteria cells. It causes derangement of their cellular structure, which is really what cancer is going to be. And that's what kills those germs. So we can use them for that. We do also have another one that's a slight bit down the spectrum. That's going to be your sun lamps or tanning bed lamps. And you're supposed to be wearing like those little eye caps over top of your eyes if you go into these things because it's very bad for your eyes. But it's going to go and give you, that UV radiation. Okay, energy efficient lamps and stroboscopic effects. Yeah, we'll cover those ones off here yet. We've still got some time off of this one. Energy efficient lamps have just got improved phosphors. The original phosphors that we had were pretty good, but we have got some improved types of phosphors that are able to pick up and carry that energy longer. Those are going to give you your energy efficient, so we need less current traveling through here, and we're able to convert more of this UV into just better visible light. And then stroboscopic effects are going to be something that is less common these days than what it used to be back in, probably more the 80s and the early 90s than it was towards the 2000s because we were already getting to higher frequencies. But stroboscopic effects is going to be the same as using like a timing light to check vehicle, where you've got a really high flash and then a low flash. And what your eye does is your eye kind of captures that, and it can appear that something is standing still when you're looking at stroboscopic effects. If you're driving on the freeway, anytime that you're driving along Highway number 1 by Abbotsford there, right by Sumas Way, there's some dividers that are right along the side of the freeway. They got these little green fins on the top there. And if you're a passenger, not the driver because you should be paying attention, but if you're a passenger and you look over at a car that is traveling along one of the parallel roads, and if you look through the green dividers, you'll actually see that the tires sometimes appear to be going backwards or that they appear to be hardly moving at all. You know they're moving, but it's just that stroboscopic effect because you're just getting an instantaneous glance, 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 and then you're blocking out part of what's happening as well. This used to happen with some of our fluorescent lights that were operated directly off a system frequency, in other words, off that 60 hertz. And because motors and so many other moving pieces of equipment are also reliant upon their frequency, right? F is equal to P times N over top of 120. You remember that formula? That means that they're also going to be operating at the same frequency. So we can get some really dangerous effects where pieces of equipment fully lit by fluorescent lighting. So we're talking about like the inside of the bowels of your building, inside of like a machinery room or something where you have no natural light. If you got natural light on there as well, you're going to be fine. If you got incandescent light, you're going to be fine. But where it's, just a room that's sealed off and only had fluorescence, you could have pieces of equipment that would not only appear to be running slowly, but they could actually appear stopped or even to be running in reverse. And if you're unaware of that, you might do strange things like shove your hand into it because you think that thing is not operating and bling, there goes your fingers, right? It's a bad time. So we have to be very careful of that. A couple ways that they could deal with that. One of them was going to be lead lag ballast. That was going to have two lamps inside of there. One lamp that would come on first, then the next lamp. So they'd be kind of alternating, wee, back and forth like that, which meant that we always had one that was going to be high. The other one was to go and place an incandescent in the room. If you ever run into a area that has got moving machinery and there's some fluorescence and there's an incandescent inside there, there's a very good chance that that incandescent was put in there to deal with stroboscopic effects, because the incandescent is literally heating that tungsten to the point of glowing. So that's going to go and maintain that. These days, if you use electronic ballast, you don't have to worry about as much, because electronic ballasts operate at ridiculously high values of frequency. We're talking, 20,000, so like 20 kHz and above, which means that the electrons that are moving back and forth, rather than this just being 120 times a second, half in that direction, half in the other, we're now going to be doing that 20,000 times a second that we have the frequency, which means we're actually 40,000 times a second that we are changing direction. So it's a really, really rapid back and forth, back and forth, back and forth. And what we're able to do is we're able to use smaller amounts of current, less electrons, because those electrons are moving so fast that there's just, ding, 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 back and forth between those pieces of mercury, which means that we're emitting a lot of UV radiation off of a smaller amount of current flow. This is one of the huge reasons why we have gone to those electronic types of ballasts. All right, let's go through these tables here. We're just going to go and take a look at some stuff that's going to be off there. Couple of things that we should be familiar with. Efficacy. We talked about that earlier. That is going to go and be the amount of lumens per watt that you're going to have. You're looking for high values of efficacy. Your highest efficacies these days are usually found inside of LEDs. Fluorescents do still need a fair bit of heat, and they have a fair bit of losses inside of their ballast as well. We've also got this, which is going to be my CRI. CRI stands for Color Rendering Index. Once again, this would have been covered in first year when you took a look at the human eye and stuff, but it's going to be how accurately it goes and shows colors. Think about, if you've got a red light headlamp, and you put that red light headlamp on your side of a dark room, everything appears to be differing shades of red. It's got a really poor color rendering index because everything is unnaturally colored. Whereas if you use a white light, you're going to get a more natural look to each of those colors. But it's still not necessarily going to be perfect. If you ever ordered stuff off of online and then it gets there, you're like, that's a different color than I expected. That's because, your monitor color was maybe different than the color that it took with a picture of, etc. It's all color rendering. So the higher the CRI that I'm going to go and have, the better the look that I'm going to go and have. What they go and use for CRI to reference is they use outside daylight, the sun. That's our most natural light that is out there. So this one over here is going to be about 82% the same as the sun. Most of us, don't recognize it very well, particularly among males. We've got a really high incidence of color blindness. So 82% to 100%, those colors would probably look identical to me. But I can definitely tell once I get down to something that's going to be like into a 60 CRI that everything just seems a little bit off inside of there. All right, input watts off of these charts here. We're just going to go through the first one over here. What we have is we have got lumens that are going to be the rated amount of lumens for that lamp. So this was an F40 T12 Ballast, and it's a pre-1995 one, so it's an older one. It took 40 watts. The F is the fluorescent, the 40 is the 40 watts. The T12 gives me my lamp diameter that I'm going to go and have off of there. CW, hold on a second. I'm trying to remember what the heck CW stood for. Can't remember what CW stood for off of that one, but not really that important because you're just matching numbers anyways in the trade. This is what the lamp should do. Then if I were to go and use a standard magnetic ballast, it was 92 watts to go and run two of these lamps. If I was going to go and use a EE rating, which was a higher rated magnetic ballast, it was going to be an 86 watts that I needed. And if I had an electronic, it was down to 78 watts. We have fewer losses inside of those electronic ones. And then it also showed me my lumens output. Now we see that this thing over here should be, 6,100 lumens, but there is going to go and be losses. We're not able to actually achieve that. That was a theoretical amount. So these ones over here are going to go and have different values. You note that the higher up in my lumens that I'm going to get out, the worse my CRI is going to be. Generally because the higher up that we would get, the more towards the blue range that we would start to go and establish that lights, the light color, because all of your blue lights are going to be super high frequency. Your red lights are going to be lower values of frequency. So those lower values are going to be seen as being a slight bit more natural, right? Outside light is generally considered to be a warm type of light. All of these are going to go and be done the same way. This is just a continuation of that same table. This one over here, they talk about different types of lamps, the ordering code that you would go and have, the base that it has, you know, so you can match it, whether it's going to be a double recess, double contact, medium bipin, single pin, four pin, etc. that we will have off of these, but the 4-pin is really just limited to those circline tubes that we have down there. Operating value of voltage, so the approximate amps, and then the operating value of voltage per lamp that we are looking at. These ones over here, you'll note that these ones are anywhere from about half to maybe about a third of the voltage that they need to see, which means that sometimes these ones would be able to be operated in series that we would go and have. Minimum starting volts, which are going to be a little bit higher, and then average preheat amps that they're going to have. You'll note that the preheat amps are usually going to be higher, once again, than the operating. 0.15 of an amp compared to 0.135 of an amp that I'm going to have. And then on some of these, they give us a nominal cathode preheat voltage over there. That's that difference going across from pin to pin that we've talked about before. All right, the last one that we're going to take a look at is going to be the low-pressure sodium lamp. Low-pressure sodium lamps are an older technology. They were a highly reliable technology, and they're a fluorescent technology. Although oftentimes people want to class them in with the rest of the HID fixtures, you know, the high-pressure sodium, the merc vapor, the metal halide, they are a type of fluorescent that we are looking at. So we'll treat them here inside of our fluorescent. What we see is we've got a complete tube inside. It goes across from end to end over there. Inside either end of the tube, we see that we have got a cathode that we are going to go and have. We see that we are going to go and have supports inside of here. We have a couple of these little sodium retaining reservoirs because we're going to be using the salts inside of these. And then we've got an outer glass envelope that goes around the whole thing. We evacuate it. So we suck out all the air, which means that if there's no trapped air, we cannot have any easy transfer of heat. Either we can't transfer coldness in, nor can we transfer heat out. And we do that to go and maintain heat inside of these things. And then at the far end, there's also going to be something that's going to just support this because it's a fairly long tube that we are going to go and have inside of there. What we will do is we will have a bunch of sodium salts that are placed inside of here. When we go and ionize gas through here, going from one end to the other, we're going to go and react with those ones. And when we do that, we're going to go and put off a type of light. It's going to be a really, really yellowish glow because we've got a fairly large amount of neon. Neon always glows in the warm range. But then we've also got the sodiums that are part of it. I don't know if you've ever seen those videos on YouTube where they take a pickle. You've done that? You take your warty old pickle, and then you're going to go and take 120 volts off of a cheated cord, and you just take that 120 volts and you place it over from end to end. And when you do that, there's actually going to be light that gets generated off of that pickle. And it's just arcing that's going through there. But the light that you'll get is going to be a very orangey, yellowy sort of light that comes off of them. And it's due to the high amount of salt. If you've ever eaten a pickle, you know that those things are salty inside of there. And that's part of the preservation process, right? So you get all of the salts inside to give you that really yellowy light that's inside of them. Same with these ones over here. They're very much similar to those pickle lights in that they're going to be a super, super yellow. In fact, they are so yellow that we do not even rate them as far as CRI, color rendering index. We just say, everything under there just appears to be different colors of brown, orange, and yellow. We don't actually know what color anything is. Back in the old days of teaching in class, you know, we used to actually fire one of these up in the class. We'd shut off all the lights. I'd take a whiteboard marker. We'd stick a couple of colors across the board. And then when we would turn off the room lights and turn on this one, you couldn't actually tell what color was what. It was all either brown, orange, or black that the colors were. What they do have is they have got a very, very short restrike time, and they've got a very high efficacy amount of lumens that I'm able to go and get compared to my watts. These were going to be in efficacy that was going to be sitting up there in like the 200 range, which used to be an incredible one. We are getting way higher these days with LED lighting, but that used to be absolutely incredible. So we would use them for areas that needed security lighting of a fairly large amount of light, and where we were looking for movement. You probably have seen these around the perimeters of prisons. If you've ever driven by any sort of a prison, what you'll see is they've got the fences that go around the outside, and then what they'll have is they've got these cables that kind of go between towers on the fences there, and hanging from those cables, they're going to go and have a whole pile of these really, really yellowy long lights. They've also got other types of HID lights, that they light up the yard and the area around the fence with as well. But the reason that they have these ones in there is those other HID lights take a long time to restrike. If there's a power outage, they would want to go and have lights on instantaneously. These ones come on instantaneously once again. The other reason that they like this yellow color is that the human eye responds really, really well to light that is going to be around the 555 nanometer range, which is going to be kind of a yellowish, almost greenish sort of color. If you ever watch late night television, they have those old person yellow driving glasses that you can have, and you're like, oh yeah, I don't need those. But then you go out and buy the yellow tinted snow goggles when you go snowboarding, because it helps you to go and see movement and differentiation, right? That's what yellow light does, is it helps you to see just small things, not necessarily color, but you can see shape and form really well, because most human eyes are tuned to that. So security lighting has used these things extensively in the past because it helps them to pick up movement, and they've got that instant restrike that you are going to go and have. Outside of that, we don't have these used in a lot of places, just because it's such a sick yellow light. Most people don't want to see it. They want to have kind of a pure whitish type of light. But yeah, you'll still see these around in some areas. They are not good if they get too cold. That whole outside shell, if that outside shell develops any crack and there's any air inside of these things, they will refuse to light because they just cannot sufficiently hold onto heat. All right, that is going to be the end of Learning Task 1. Is there anything that I missed that I wanted to talk about? Not really. I mean, we talked about disposal. At the very end of these ones here, they talk about that these ones have got a high amount of sodium metal. Any type of fluorescent, doesn't matter whether we're looking at a regular fluorescent or HID fixtures, should be properly recycled, because the substances that are inside are hazardous. And first of all, we don't want to dump them into the environment. Secondly, it makes the rest of our industry function much better because it's easier for them to be recovered and put back into new components. All right, that is the end of the Learning Task 1.